Hi everyone, this is Project Group 24, and our project is on a machine learning mesh-aware upscaling process between a low poly render to a target high-res render without the additional computational costs of the high-res render. So the first step we have to see is how we did the low-res, low-poly render, why we did that, and the kind of visual techniques that we use to achieve this.
So basically, the technique we use to obtain a low poly render is mesh simplification. Essentially, by taking the high poly render and removing a number of vertices, we were able to obtain a low poly render. And if you were to take a look at the code, since removing vertices results in gaps in the model, we calculate new faces and flat normals. And essentially, these methods are similar to how 3JS handles mesh simplification. And by doing this, we remove all the gaps in the model.
That is the first and very crucial step in our rendering pipeline to generate a both computationally less expensive, since we don't have to calculate the lighting on the much more additional vertices. And also we use the low resolution nature to help with that as well. And so the next step of our project is getting this low res, low poly render to the high res, high poly render. And so let's talk about how we did the machine learning upscaling.
So for the upscaling, we use diffusion models. Diffusion models are basically ML models that gradually add noise to the data in a controlled manner. In our project, our goal was to learn how to reverse this process to start with random noise and reconstruct the original data step by step. Going over the code for our data, we used a PyTorch-based implementation of a diffusion model designed for tasks like super resolution. The model that we used had 4 key components. The first one was the linear noise schedule. The second one was the diffusion process. This function generated the noisy image for the given timestamps. Then we had the sampling process, which is the reverse process I talked about, where the model progressively denoises the image step by step. And the last step was the training step, where we used multiple loss terms to guide the model's learning. If I wanted to summarize all the 4 steps, so we start with a low resolution input image, we upsample it to the target resolution, we use the model to predict and remove noise over a sequence of steps, and then finally in the end, we incorporate the final details like edges, color corrections, etc.
And that is an overview of how our upscaling works, but how it actually gets from the web to the upscale Python is that initially we plan to import the machine learning model as said in our proposal to an entirely web-based system. However, we ran into a problem in the sense that this is not just a one-shot image-to-image model. Instead, we need to go through the entire diffusion process, as well as this model using around 9 gigabytes of video memory, which is not feasible to do on a consumer device. So instead of our original idea, we now have a server that provides this information. So we take a low-res screenshot we gathered, we send that to the server, and then the server gives out each step of the upscaling in frames. So for each upscaler, we send 20-ish frames to the main web app in order to visualize that process. And to demonstrate, we can again look at, for example, this teapot. So you can see this teapot, especially on the outer ridges here, it's very pixelated. If I can zoom in, these pixels are very apparent, and it doesn't look like a circle at all if you look at this bar too. But with our upscaling, so we settle on 100 steps because that's a good balance between the model taking a very long time as well as generating a relatively decent image. So our upscaling isn't perfect, but if you zoom in, you can see that the edges are much rounder and more consistent with the real high-res rendered image, whereas the original low-res, low-poly model, as you can see, is very pixelated, and there are much more artifacts than in the machine learning-based rendering. My name is Tom.
My name is Raghav.
My name is Alex.
And we're Group 24.